Our next speaker is Barb Thomas, a professor and industrial research chair in tree improvement at the University of Alberta since 2014. Her chair is supported by 10 forestry companies and the Alberta government. She previously worked as an industrial scientist in Alberta for 17 years and is an active and founding member of the Tree Improvement Alberta, where she is on the scientific committee responsible for the Alberta Forest Genetics, Resource Management, and Conservation Standards of the province. Her presentation is entitled, "What Role Can Tree Improvement Play in Meeting Our Fiber Needs?" Welcome, Barb, and I will get out of your way. Neil, get yours. Thank you.
So is my screen working? I'm going to take that as a yes. Okay, thanks very much. Thanks, Vic, for the introduction and also the invitation to be here today. I think so far it's been fantastic, and the previous speakers have set the stage well for what I'd like to say in terms of where tree improvement and fiber fits into this picture. So with everything, I think in life, we often have lists. So I thought I would just throw up a bit of a pro-con list. Tree improvement is not a panacea, but it has a lot to offer. Obviously, the main reason that everybody got into this was to look at increased volume per hectare on the land base. However, with that comes a long-term financial commitment. We have the ability to select traits beyond just height and diameter now. And in fact, I think we have to go beyond those basic traits now. And this does require specialized expertise as well in some instances. One of the big pros is the opportunity to allow for adjustments to climate change by understanding the parents in our programs and understanding what kind of traits they have within those populations. And with tree improvement, regardless of the climate change issue, we already have larger areas of deployment that are possible with the same seed lot because of the testing that goes on associated with them. I'm not sure our tenure system in Alberta really helps very much in regards to some of these aspects, and the timing, planning horizon being relatively short relative to the time tree improvement takes. But half our programs are run by industry approximately, and half our programs are run by government, which is a bit of a problem in my view. One of the other pros is regular seed supply. You can get rid of the ups and downs of spruce masting years. You can get a long-term supply of black spruce, for example. But there are always trade-offs in these orchards. Do we leave trees, parent trees in the orchard that aren't really contributing very much, but do contribute to seed supply, but they don't contribute to volume? Do we cut them out and reduce our supply with higher quality seed? These are some of the trade-offs. There are some ways around that, of course. And there's some new genomics technologies available, which we're right at the edge of being able to grasp and move forward with. Gain is perceived to be quite low, and yes, some programs are low, but others have really moved ahead, and we're right at the point of being able to move to second generation orchards. Honestly, the hard work is done. There's been decades of investment, and we can really capitalize on that now and move forward. With that, of course, comes increased monitoring requirements. But one of the biggest pros, in addition to the ones listed above, is a secure fiber supply. However, on a pure dollars and cents side, it might be considered a low return on investment. So to parse this down to a very simple version of where I see this, as the pro is flexible security. Where we put it, what we put, how we put it, and even when we put that material. And on the con is this long-term economics. And that's for everybody, whether you're government or industry. So what's tipping the balance here in terms of what we do, how much we embrace and adopt this? On the left-hand side here, we have a picture showing the drought years ever increasing. Any year that goes below the 0 mark here is considered not sufficient moisture to sustain a closed canopy forest. this is becoming challenging. We have our climate change issues in addition to drought that are related to insect attacks. On the pure tree improvement side, over on the right, we have our age-age correlation. We want to make selections when trees are young, and we want to project to what they're going to be like at rotation in terms of size. The red line shows 10% gain without trying to make a guess that you say small tells you exactly about large, whereas when you add in a correlation that reduces that, of course, it brings down that total top height and ultimately the yield. Is it just a dollars and cents, or are we really after that fiber security? If you take this in its simplest form, you have these three components. You have the genetics, which we can shift through breeding, through selection. We have silviculture, which we can apply in many of its component parts. And we can choose our sites. If we put these together in the right combination, we can maximize those gains, which can be realized in two ways. If you're talking purely about volume, you can increase the volume for the same rotation age, or you can drop the rotation age for the same volume. So here's a couple of examples. In white spruce, this is some work that's been done by my PhD student, Dawei Liu. On the x-axis, we have stand age. These are pretty standard looking curves for most of you, I'm sure, and volume. And this is being with a scenario for the white spruce with selection age of 15. So we have total volume in the solid bars, and we have merchantable volume in the dash bars. The black line is unimproved. The purple line is 10% height gain. So if we take a scenario where we want to harvest at age 85, we could get 200 cubic meters per hectare in the unimproved, or 222 in this is merchantable again, in the improved 10%. Or we can delay for the unimproved stand 6 or 7 years to get that same yield. So these are the kind of trade-offs we have. For lodgepole pine, the curves look a little bit differently, and the age-age correlation isn't as strong between young and harvest age trees. And in this case, the selection age is at 25 in the progeny trials. And you can see, again, this is merchantable volume and total volume. And we get the same basic scenario here at 70 years. And if you expand it out to any number of hectares, you can easily do the math to see what the benefit is of having these different percentage increases in genetic worth. Andy happened to send me some information this week that actually fit in very nicely with being able to present to you. And this is what's going on in terms of our seed use in the province for white spruce and lodgepole pine. On the left, we have white spruce. On the right, we have lodgepole pine. And the orange line is stream 2, which means seed coming out of our seed orchards. The blue is stream 1, or our wild seed coming from seed zones. And you can see that there's a crisscross happening here with quite a significant increase in the use of white spruce seed out of orchards. The gain out of these various programs ranges from 1 to 8.8% for height at rotation, with the mean at 4.4%. So you have to remember that there's a multiple of 2 in here to move essentially from the height to volume. On the pine, we haven't done so well. There's some challenges with these orchards with cone-lid abortion, and to move between the sort of 15 and 20% is where we're at. And again, there's some pretty significant gains starting to come in that 9.3% range. So how do we look relative across Canada? This is the annual seedling deployment in millions. So BC, of course, at the top there at 250. This is from 2017. Alberta in at 87 million. And you can see Quebec here is somewhere in between. Now hold these thoughts in your mind as we move to the next slide. And in this, we are looking at seed orchard area. So the amount of land that has seed orchards planted onto it. And this is between 1988 and 2017. quite a big investment change here in BC. We do have a doubling here. However, if we were to match the same amount, which is around 70 to 80% of the reforestation in BC, if we were to match that, we would need about 126 hectares of orchards to keep pace with what's going on in BC. So we are way behind here in our orchard installations. I talked about flexibility. So this picture on the right shows the breeding zones or controlled parentage program zones for various white spruce programs in the province. And these triangles denote the testing areas. And on the left-hand side, the subregions, and we have 90 seed zones in this province. And so the point of flexibility as to where you can plant this seed is, let's take the G1 example here. It's this large area here relative to here. So you can see there's huge flexibility in your planning from a silvicultural perspective as to being able to move that material and also address climate change. The last point I want to make here is around this whole process. It's time consuming. This is a figure taken from a paper. It's actually from loblolly pine, but we can use it as an example. There is a phase of breeding or collecting from the wild for first generation. It takes a few years. Then there's this long testing phase. 8 years, of course, is not what we have. We have closer to 20 or 30. And then this propagation or production of seed. There are places where we can truncate this down to much smaller time periods. But this initial 30-year investment is critical to be able to do that. We can move to a scenario where we are reducing down that testing through technologies such as genomic selection. We can reduce the time for breeding by doing what's called top grafting. We're not really doing the clonal propagation here, so I'll leave that one alone. This is just a picture of Deanne Renaud doing some breeding in the pine, lovely pine conelets, and here's some work with looking at different breeding bags, and the top grafting is where you have a different genotype grafted onto the top of a mature orchard tree to be able to go more quickly with that flowering and breeding. Genomic selection, you can get more information about this if you check out our website here with our Res4 project. This is where we take traditional, conventional breeding, we capitalize on that, and we move through looking at the DNA sequence and relating that sequence to the phenotypes, the measured height, diameter.
Barb, have you got a couple of
This is it.
summary?
This is it. Do the pros outweigh the cons? So recent investments in Alberta have paved the way for technology adoption. We can speed up our decisions. We can adjust to climate change. We've got specialized training in the works. We need to retain those people now before they leave. The cost of genotyping is less expensive, actually, than measuring these trials. And there's the need for the flexibility to secure, maintain, and ensure fiber supplies with best practices in silviculture. It's incremental. The genetics is incremental.
Okay.
And that's it.
Thank you very much, Barb. That was very good. So I think we have to move on to our next speaker.